So, hi everyone. Not everyone is sitting yet. I won't wait because we have a lot of slides and we have to make it fast. You know, we are making a server, so we are used to be fast. My name is Daniel Katz. I'm a developer on the Helidon project here in Prague in Oracle. And my colleague here is Tomas Langer. It's the architect of the Helidon. It's like the mastermind behind everything. So I will introduce it and we'll let Tomas. You all know how to access Slido, right? So I don't have to spend time here. This is us again, sorry. So here is the agenda. I will, okay. There will be a short Helidon introduction, what we are, what we do. We have some flavors of our Helidon, so we will also introduce them. We will take a look at some main issues we are solving in the Helidon server for us. How we are optimizing the server concurrency, which is a big issue for the servers. We will take a look at our reactive Helidon. Then we will take a look at the virtual threads, which is expected, right? And then we will take a look to another flavor of Helidon, which is Helidon Nima. We will also show how it affects the Helidon MP, which is annotation-based flavor, another one we have. In the end, we will take a look at one of the main issues of when you are using virtual threads, and that's the pinning of the thread in some special cases, which is very important for us in the server. And if there will be time, we will take a look at some challenges we had when we have been implementing the Nima, but we have a lot of slides, so those are kind of optional.
Okay, I will take over from here. So I will say a few words about what Helidon is before we dive deeper into virtual threads and how we tackled that problem. So Helidon is a framework for developing microservices. We say quite a lot of times that we are also a set of libraries because we have libraries that you can use standalone. Helidon is comprised of something like 340 modules. And modularization is one of the core things that we try to keep as small as possible, so you don't need to have 20, 50 megabytes of data just to write a very simple service. By the way, the smallest service you can write with Nima, for example, is 1.5 megabytes total dependencies. We are Kubernetes friendly. We try to write our stuff in a way that you can easily deploy it to a Kubernetes cluster or to any other container managed environment. One thing that is related to the size of our libraries, we try to keep them small, but we also try to keep the dependencies to a minimum from when it comes to third-party dependencies. So we do not use any other third-party logging library. We only use the JDK. And we are currently switching to System Logger, which also supports replacement of implementation, so you can use it with your Log4j or simple logging framework for Java or Logback. And this is actually valid for anything in Helidon. If there is a feature in the JDK itself, we will use it, rather than writing our own. It has an advantage when it comes to size. It also has advantage when it comes to security. As we have seen with some of the attacks coming, for example, on Log4j, we were not affected because we just don't use it. We do have multiple flavors, and I will talk a bit about that on the next slide. So our basic, and the first thing that we implemented, the basic flavor is Helidon SE. It is a reactive implementation. And if you have been on the previous presentation on virtual threads, reactive has one big disadvantage. It is very hard to handle. It's really fast. You can develop heavily concurrent microservices, even in the current world where we cannot block on a thread, but you pay for it. You pay for it with maintenance, debugging, and of course the learning curve. Opposed to that, we have Helidon Microprofile, which provides that ease of use for a programmer. You can use annotations based on JAX-RS. The core is CDI. So the imperative design is easy to write. It uses Helidon SE, the reactive web server, under the hoods. But of course, there are also some trade-offs. In this case, it's a blocking environment. So if you block, you cannot do as many concurrent requests as you can do with a pure Helidon SE implementation. This doesn't mean it's useless. There are a lot of applications that do not require tens of thousands of requests per second. And for these applications, you actually want to use something that's easy to write. So we provide both of these worlds. And of course, something new is coming. We are really interested in virtual threads, and we will talk about that quite a lot. So now, I said that Helidon is really targeting the, quote, cloud-native environment. We want to be as good in a container as it's possible. And for that, we also define our packaging. So you can actually do 3 possible packaging with Helidon. First one is Helidon executable jar, which is using the hollow jar approach. Hollow jar means that there is a very small jar which with only the code of your service, and all the third-party dependencies are in a separate library, in a separate directory called libs, and it's referenced through meta-inf manifest. So when you start your application, it will use all the libraries in the directory. The reason is that you can create a Docker container with a layered file system where your third-party libraries are in a different layer. So if you need to update your application, and you don't need to change your third-party dependencies, the update is really, really fast when it comes to deployment on a remote server. Second possibility is JLink image. JLink is a feature of Java that came with the module system. Helidon is fully modularized. Every single module that we have has a module in for the Java. And we also created a custom implementation for JLink construction where we analyze even the libraries that are not modularized to create as small runtime image as possible. So JLink basically removes the modules that you don't use and creates an application-specific Java runtime environment. The last possible packaging is GraalVM native image. GraalVM native image does an ahead-of-time compilation of your code into a native executable. So that's for the cases where you don't want to have a Java runtime environment at all, and you can directly run that native image on Linux. And there are several advantages to native image, such as closed world. So security is much higher. It has very fast startup time, because everything is already precompiled. There are some disadvantages. You don't have just-in-time compiler, meaning that what you compiled at build time is what you have, no optimizations at runtime, so it tends to have lower runtime performance. And again, all of these packaging can be easily containerized and deployed to Kubernetes. So I will give it back to you. What problems we solve?
Yeah, I'm good for problems. What problems we do solve in the servers? That's usually a very heavy concurrency. That's a problem each server in the world needs to solve because there is a lot of client connecting and it needs its response as fast as possible and so on. So that's what each server needs to handle. And those servers also need to do something else. So if we are using some threads, we need to, from those server threads, you usually want to do some work with them to call some other systems and so on. So this is what we are trying to do as fast and as easy as possible for the developer. We have to create it fast. We have to spend as less as CPU as possible, as less as memory as possible, as less of everything as possible. We just need to optimize and optimize and optimize, so you don't have to that much. Why? Well, it's a cloud age, right? So your managers actually can see the cloud bills and they can see how good developers you are because it costs them directly money and it's visible almost immediately. So when you want to start to create your microservice, you have to choose right technology to actually be as fast as possible when you start, and then you can optimize your own code from some nice starting point. What is expensive in this highly concurrent environment? Well, of course, it's concurrency. That's the thing when you can save a lot. And with Java, it's kind of complicated because in Java nowadays, each thread you create is actually a wrapper around the kernel thread, the physical thread in your operating system. And this kernel thread is very expensive to create. It's hard on memory because it needs megabytes each thread when you create it. And also, you can't create really a lot of them because the managing of those threads costs something, and the more threads you have, the more expensive the managing of those threads is. And that's another big issue, and that's the context switching between the threads. Because if you have this CPU, you know, there is more threads actually competing for this one CPU, and each of them needs to do some work. So your operating system actually needs to schedule them right, so each of them can work for some time. But when he's doing this, he actually needs to clean up all the registers from the old task, save the data somewhere, and bring the data from the next task to the registers, and then the work can start. So more threads you have, the more expensive this context switching actually is. So those are the two issues we have with the concurrency. Creating a new kernel thread is very expensive, and context switching between those threads is expensive, and it gets even more expensive when you have a lot of kernel threads. So how is it being addressed? Well, for some decades now, we are using thread pools. If everybody knows the thread pool, you are not creating a new thread for every task, you are just reusing the threads in your pool, and that way you can actually achieve that you don't have that much of the thread and you don't start as many of them anymore. The second issue is the context switching. And with the context switching, we actually can also do something. We can minimize how much is happening by avoiding blocking the thread. Because if you are blocking the physical thread, you know, it will yield, and some other thread will get its chance, and they will change on the CPU. But if you don't, if you keep your thread working all the time, you will minimize the number of the context switches, and you will perform much better. You will squeeze more from your hardware. But how? How can we do that? We are doing that for quite some time with reactive programming. That's an asynchronous approach when you, instead of blocking, waiting for something, you actually register some callback, and the other side will call you on different thread when it's actually done. And your thread can go back somewhere into the event loop and work on something else, serve to some other client of your server. You all know the callback functions. You also know what happens when you have too many of them. It's called callback hell, right? When it's being called and there is no order of things because everything is happening different times. The chances for the race conditions are just getting higher and higher. We also, with the blocking, when we ditch the blocking, we have also lost the back pressure. So you can actually control how much data will come to you from those callbacks. For all of this, we have extra API. It's reactive streams, which is trying to orchestrate those callbacks into some more comprehensible way. So you have some rules in which they are being invoked, and you can actually think about it. Well, reactive streams, that's the API for orchestration of callbacks. We already said that. It has built-in back pressure mechanism, so the downstream, the receiver is actually can actually asynchronously ask for the data and how much data he actually can get, so he doesn't get overflown by all the data from the callbacks. The reactive streams has been part of the JDK since Java 9. It's the famous Flow API, but they are only the interfaces there, and they do look fairly simple. So one even would like to implement it himself, but it's very dangerous. It's very dangerous because it's not only the API, it's also the rules. There's a specification for the reactive streams, and the rules are really, really complicated just to bring the order into this callback hell. So it's very hard to implement it right. It's so hard that actually IntelliJ will actually warn you if you try that, that you shouldn't, and you should rather use some of the existing implementations. There is a lot of them, actually.
I'll just say one thing here. IntelliJ is right.
Yeah. So there is, everybody knows Eric's Java from David Carnock and those Netflix guys who've been helping him, right? There is Spring's Reactor, everybody knows that. The Apple has its service talk. We have our own operators in Helidon, but they have been actually contributed by David Carnock also. It's kind of different version of the Eric's Java, but from the same guy. Quarkus has Mutiny, right? So there is a lot of implementation you can choose from. So don't try to implement it yourself. It's very hard and it's very expensive to create your own implementation. But you can use a lot of options out there. But those operators are actually making it usable, right? Well. How many of you here are actually working with the reactive programming, using the reactive operators? Yeah, quite some hands there. I also have this Stockholm syndrome, and but this is more real-life example. This is the Helidon SE. This is the reactive handler of the web server, and if you have the HTTP call with GET, REST call with GET, this handler will be executed. But you cannot block this thread, obviously, because in the event loop there is like 4 threads there. So if you block one of them or 4 of them, your server would just become unresponsive. So instead of that, we will use our reactive HTTP client, which will call another service, but we will use the thread only for creating the request. And then when we create the request, we won't wait actually for the other side to respond, but we will register the callbacks in this reactive streams to be executed on the different thread when we get the response from the client. And in the end, as you can see, it will be the client's thread which will actually send the response from our server. As I have already introduced to Helidon SE, there is it's a reactive web server. It has a lot of other reactive tooling available just for you, so you don't have to block anywhere. We are really trying to make it as easy as possible, so you don't have to block anywhere. You just use this event loop. It's built on top of Netty. A lot of you probably know this library. It's for communication over the network asynchronously, and it's one of the fastest implementations available right now. And we have our own operators, which are somehow special because we are also compatible with the completion stage. Our reactive primitives, like the single there, can be actually used as a completion stage when there is API required, and you can just pass it out. So the transition is very, very easy. But reactive programming, it has a lot of buts. You can implement your own subscribers. Well, you can, but you shouldn't. It's really hard to. It's really hard to implement to learn it and learn it right. And if you already understand it, it's really hard to maintain the reactive code. It's really hard to debug it because with the debugger you are just jumping over all those callbacks, and the stack traces doesn't make any sense because, you know, even in that example before, on one line you have a stack trace which leads to the web server, and on the other line you have a stack trace which leads somewhere into the client. So it's very complicated to actually find a bug, to maintain a code you inherited from some other guy who left the company 5 years ago, right? If you want to block there, it's impossible. You just need to start or use the physical thread and block in there, and you can just wait for it, like in this nice structured concurrency. You just have to use another callback, which will call something asynchronously, and another race condition, I don't know. And there is still a callback hell. It's smaller, but it's still there. And there is better solution. So.
Okay, so. There are a lot of problems with the reactive programming that can be solved. You can write it right, but it's not always easy to use. And one of the things that actually I wanted to add to that is error handling. Everybody who has worked with Java knows, the try-catch block, and we like it, right? Try-catch, finally you can do stuff. If you do it with reactive streams, it's absolutely useless. because the stuff that's happening in the reactive stream will happen somewhere in the future. At the time your try-catch block is executed, that's the time when you just start the request, and that's it. So if you have a wrong header, then maybe your catch block will catch it. But if the server is unavailable or anything happens on parsing of the response JSON, it's lost. You need to handle that in reactive stream. So what do we want to do? We want to do this blocking. We want to use our try-catch blocks. We want to use for cycles. We just want to use Java, right? And the solution for that is virtual threads. It's part of Project Loom, JEP 4.2.5, and it's finally available as a preview feature of Java 19. So now, so how many of you have been on the previous presentation about virtual threads? Okay, a lot of hands, so I will probably do this quicker. So the most important part is that we do not block the platform thread. And that's really the solution to most of the problems we have been describing before. I will just skip all of that because really virtual threads is a great thing, but for me what is really important, you can go back to the naive implementation of Java. So the stuff you learned at school, you can finally use it without the problems that it introduced before. It will be performant, it will support heavy concurrency, and it will be much easier to read, write, maintain, do whatever with it. So virtual threads came, as we said, as part of the Project Loom. The other thing that's part of Project Loom is structured concurrency. I will go through a few steps here. So first, we can block cheaply. That's very easily. Quite a lot of stuff happens under the hoods. And I honestly like that. I don't want to know when I am executing on a carrier thread and when I'm waiting for some remote party to respond to me. Java knows, so let it handle it, and it will handle it right. And the real thing here is that we can achieve the same performance or comparable performance to reactive with blocking. I will let you explain the green threads because that's the part that...
Yeah. There's always a question. We already had the green threads in Java, right? It was in the Java 1.2, so not everybody remembers it. But it was very similar. There was a M to 1 mapping in the Java. There was you could have those user threads in Java, which were lightweight. It was created in Java, and it was scheduled on top on a single thread. It was in the times when the JVM had only one thread. It was single-threaded, and it only simulated the multi-threaded environment. Obviously, when the Java 1.3 came, it got ditched because there was already a multi-core machines there available, and everybody knew that the single-threaded applications won't work right. So it's not the green threads this time. We really have the M to N mapping. We have multiple, maybe even millions of the virtual threads mapping to the multiple platform threads. So it's something very different than the green threads was. That's before anyone asks. Yeah, and we are back to our example. You still remember it. It's reactive. We cannot block the thread, so we register the callbacks, and the client's thread will actually send our response. This is how it's done in the Helidon SE, which is reactive, and we already have this Helidon Nima, which is built on the virtual thread, and it's completely imperative, and you can block whenever you want. So the same thing you do just like this. We have the server handler on the virtual thread, which you can block whenever you want. And we have blocking client, which will actually wait until we get the response from the other server. So when you go with the debugger over this code, you will actually go from the up to down, row by row, and it will have the right order of the things. And the response will be actually sent by the same virtual threads like the one which you have started.
So maybe we have a comparison side by side here. On the left side, it actually looks very nice. Like it's kind of neat. You have like a stream of the commands that you are executing. But really, the most important part is maintenance. We all know, like everybody who works in a company that is developing software either for its own needs or for somebody else, you do know that you develop the code, the initial development is like this tiny piece of what you do. And then you have the huge piece of maintaining it, improving it, adding features. And yeah, you will know what you have written at the very time you have written it for reactive. And then the next day, you will spend half an hour trying to find out what actually happened. And honestly, this is a simple example. This example just calls a service, then does something with the response, and that's it. Now imagine that you want to call 5 services sequentially, or you want to call 5 services in parallel, and you need to handle that in reactive environment.
Flat map.
Yeah, and you start using the flat map operator, and you need to understand what is happening under the hoods, because otherwise it will not work the way you expect it to work. So definitely for maintenance, you will realize that doing imperative code is the right way to go. So now let's have a look on what we did in Helidon. I always start this with, when I learned that virtual threads will be a preview feature, I said to my managers, we should really look into this. This looks interesting, and I think that if we can reach the same performance, or at least similar performance as Netty, we should implement it and we should use it. And we did the first proof of concept, and we are now half a year later announcing that we have an implementation available in Maven Central that you can use. It just requires Java 19 preview features. So, it does work. It's a server designed for virtual threads. It was implemented in cooperation with the Oracle Java team. And yeah, the performance is comparable to Netty. We also plan to have it as the heart of our next major release, and this highly depends on Java team and the availability of a long-term supported release with virtual threads as a production feature.
Should be September 23.
Fingers crossed. We cannot influence when that happens, but definitely we hope for version 21. Okay. I'll let you talk about the features a bit.
Okay, we have some features in Nima. We already have implemented the HTTP 1 with the pipelining. We have the server and the client. We have the HTTP 2 prototype, which is already working, and we are working on the client right now. We have the gRPC prototype, the server. We don't have the client yet. We will get there. We have a prototype for the WebSocket server, and because the Nima is designed so well, thanks to our architects, it's very easily extensible to other TCP protocols, so we will be adding other stuff later. We have great test support also.
Okay, and now we are talking about virtual threads, right? So let's have a look a bit in the architecture of the threading of Nima. So first thing, we actually also use platform threads, and that's the socket listeners. The reason why I use platform threads there is because you expect to have a very low number of them. You usually have like one production port that serves your business logic and probably one port that is available to Kubernetes to do health checks, provide metrics, and so on. So you don't really have a problem with running 2 platform threads in your application. In addition to that, for each thread that is doing a server listening, there is a virtual thread open for each accepted socket. So when there comes a request, either for HTTP 1 or HTTP 2, we create a new virtual thread that will handle that connection. There is a configurable option to also have an additional virtual thread for writes, because we found out that under high performance scenarios, for example, when you use HTTP 1 pipelining, it's actually faster if you write the responses asynchronously. So you can enable that. By default, it's disabled because it's actually easier to handle, and you have also nicer thread dumps. So it's only really if you need those 4 million requests per second, then you can enable it. In HTTP 2, there is also one virtual thread per stream, and HTTP 2 stream is kind of an equivalent of a request-response interaction. So that will be very interesting when we get to the performance slide. We will first look a bit at the features that we have right now.
Yeah, we already have implemented access log, the course support. We can serve the static content. Well, we are a web server, right? We have the tracing support. We support OpenTelemetry and OpenTracing, and we have health checks. That's all needs to fit to other features we have in the all other Helidon implementation. So it nicely fits together. We will see it on one of the other slides why we are trying to align all the features together in those flavors.
If we get to the
yeah, we will.
To the last slides. Okay, so one thing I wanted to say here as well. Right now we are working on additional stuff in Nima, so all the features will eventually appear on this list. So now let's have a look at performance. I always say that you need to take the numbers with a grain of salt because every benchmark that you create is biased. And this time the bias is that we wanted to look at the overhead of the framework, so I didn't really care that much about the overhead of the benchmarking client. So it's all run on a single machine with loopback interface and network disabled, just to see what we actually use from the CPU and memory and not care about the network performance. It also uses different Java versions because we require Java 19 and you cannot run all the things on Java 19. For HTTP 1.1, we are using the TechEmpower benchmark tests as they were available at the time I did the tests. So the Netty version is for 136. For Netty, we are using a pure handler. So there is no framework. It's just pure Netty with a handler that's written inside of it. For Helidon SE, we are using reactive routing and our version 2.5. And Helidon Nima is the latest one, which is Alpha 2. The clients that we use for HTTP 1.1 is the same client that is used by the TechEmpower benchmarks, which is WRK, which uses both. We have tests both with pipelining and without it. And for HTTP2, we use H2Load. So now let's get to the numbers. That's the interesting part. So the first column, the blue one, is Netty, and the red one is Helidon Nima. And we have chosen two benchmarks. It's the JSON over HTTP1, GET request without pipelining, and then plain text request over HTTP2 over SSL. Now, as you can see, we managed the task that we set. We wanted to be at least as fast as Netty, and comparably, we are as fast as Netty. The numbers are slightly better, but it depends really on the environment and which test you use. I didn't show here the pipelining test. By the way, we reached around 4 million requests per second there, both us and Netty. But it's kind of an artificial use case because HTTP 1.1 with pipelining is not used that much. What is important for us? Helidon MP on Nima is actually doing very well. That's our microprofile implementation. And Helidon SE, we can see that the reactive code is better, obviously, than our microprofile code, but it's not doing as well as Helidon Nima, and especially in HTTP2. And the reason for that is there is quite a lot of overhead that you need to do because Netty is not a reactive server. It is a non-blocking server. But to transfer from Netty request and response, you need to do quite a lot of code to create the reactive stream. And obviously, we could improve there. Luckily, with Nima, we don't need to do it because that's really easy. Like with the virtual threads, the server implementation, honestly, is server socket.accept. And then I get an input stream and an output stream. And I just write to it and read from it in a virtual thread. And that's it. So basically, 90% of our server code that is taking care of entity was actually thrown away in that implementation. And that really helps with performance. So this is one of the best cases where we can see that simplicity will win over complex but highly sophisticated solution. The last Drop Wizard is here just to compare because Drop Wizard is like a full stack framework that does everything. So it will always be slower because you need to do more there than we are doing in our quite simple example. So now I will let Daniel talk a bit about how is that possible. I have stolen part of that.
Yeah, I will be fast. How is it possible? It's very simple, really. That's what the virtual threads or the Luma project does for you. It moves all that things you need to do with the reactive stuff. It just moves it under the hood of the JVM. So it does exactly the same thing. You just don't see it. It's avoiding the context switches in a very clever way. And that's the same thing you are trying to do with the reactive. And sometimes it works and sometimes it can be problematic. This is the Helidon MP. So we have already talked about it. It's our imperative annotation-driven server. This is a JAX-RS endpoint. It does exactly the same thing as all those examples before in imperative way. And we have it, or we had it, built on the reactive Helidon SE. It looked like this. It was actually some abstraction layer between the reactive web server and the Helidon MP, which translates. It actually used the thread pool with physical threads, and because you just can't block the reactive threads, right? But now we have the Helidon Nima, and it's also imperative. So everything is just somehow getting together nicely. You know, it fits much better because all that's complicated abstraction, how to offload your work to another physical thread, and all the performance you lose on that just gets out of the way, and it just works nicely. So we have really nice numbers now. You can see the same. This is actually the same use cases as we saw on the previous performances, but this time we are comparing the Helidon MP on Nima with the Helidon MP on SE. And as you can see, we just got really nice numbers. And this is very preliminary because we are still working on this. And we expect the numbers go even better. And what we don't solve. This is the very well-repeated problem with the virtual threads, and that's it doesn't solve the obstruction of the thread. So if what is the obstruction? Is some long-term utilization of your thread? You are doing something heavy with your CPU for a long time, so there is actually no blocking, you know, but you are still pinning down the physical thread under the virtual thread the way it cannot be used by any other virtual thread. And if we have in our fork join pool somewhere deep down in the JVM only, I don't know, like 4 physical threads for all those millions of virtual threads on our server, it will eventually run off the threads if we do those long operations, and it will have to start another, and we will actually degrade our performance. What does the reactive code when you do the same obstructing on it? It's actually written in the spec of the reactive streams that you shouldn't do it. There is shouldn't there, which is kind of weird, but you shouldn't do it. And why? Because usually there is a web server with some event loop. There are also only 4 physical threads in it working on all those requests from all the clients your server has. But if you do the pinning there and you exhaust all the physical threads, 4 of them, your server will actually become unresponsive. You won't just downgrade your performance. It will just stop working altogether. So this is the difference between the virtual threads and reactive design. The obstruction is still a problem. You still pin the thread, but it's not such a disaster with virtual threads. And how we can work with this? Well, we have to offload our work to the physical thread. It's kind of weird, you know. We have all the talk we are talking about. We shouldn't do that. We shouldn't start a new thread. Well, if we already know that some task will take a really long time, it's pretty natural to actually offload it to the physical thread, because then the long start is you can actually use that long start of your thread, or you can use some thread pool, right? And there will be no extra context switching, because that thread will be just, you know, used all the time. So this is how you do it in the reactive Helidon. You just offload it to we have some special fault tolerance asynchronous stuff which can offload it to different thread. This is how you do it in the Nima. And note the difference, because this time we don't have any callback which will send the response for us. We will just block until the physical thread thread finishes. And this is actually a structured concurrency in its all beauty, because you just wait until all your parallel work converges into one point, and then you continue next. So there is the order of things there. You can debug it at least somehow, right? And this is the Helidon MP on the Helidon SE. You don't have to do anything, because all the handlers are already offloaded to the physical threads. It's expensive, but we have to do it with the reactive web server under the hood. With Nima, on the other side, we actually have to offload the work because we are on the virtual thread. Well, but we are in the enterprise Java, so we have annotation just for everything, right? So we will add a synchronous annotation, and it will just work. And there are some nice stories from the Nima development, but we have last 10 minutes. I don't know how many questions we have.
Before we get there, I just wanted to let me slightly come back to this picture. We said that in HTTP2, we are creating a virtual thread per request. I just wanted to show that this is an actual benchmark, and you can see that we are running 300,000 requests per second in HTTP2. When it runs on pure Nima, without MP, it will be around 800,000 when you use TLS, and around 1 million when you use no TLS, plain text. This means that the server is creating up to 1 million virtual threads per second to handle the load. I mean, that's a really impressive number, considering how expensive we tend to think asynchronous programming is. So don't be afraid of it. You really can create a virtual thread. It will not hurt you. You can get 1 million requests per second. That means you can probably handle your load. Now we can get back to questions if we found any.
Yeah, we have like 8 minutes now.
So let's see if we have questions. If we will have free time, we can still go back to some of the war stories. But
Trust me.
I like the second one. I didn't read the first one. Thank you very much. Okay, that's not a question, but it's really nice to hear that. Does the arrival of virtual threads mean I don't have to learn reactive programming to make a living? I certainly hope so. Like, that's the whole idea. That's the reason why we created Helidon Nima, and that's the reason why our team decided that we go full on this bet. We really think that virtual threads is the right solution to programming in Java, and I haven't yet seen a use case that would show me that reactive programming is better. Like, I didn't find a use case that would say, I cannot solve this with virtual threads and have the same performance.
Can I have this one? Yes and no. We are using Jersey under the hood, and because we are from the Oracle, we are actually sitting in the same office with the guys from the Jersey team. So
Jersey is a JAX-RS implementation. We are just using it. So Helidon MP is implementing the microprofile specification, and microprofile specification tells you that you must implement JAX-RS. It's one of the requirements. So we use Jersey for that. We don't implement a new one. The next question. I think that I have answered this question already. Yes, I think that's the case, that they will replace reactive programming. Why choose Helidon over Netty if the performance is not that much higher? So first thing is that I expect we are talking about the virtual thread implementation. I'm not sure if you worked with Netty directly. So first thing is that writing a Netty handler on its own is kind of complicated task. And I must say one thing, the example, the TechEmpower benchmark that I'm using, it uses a handler that is capable only of processing GET requests with very short entities. If you want to use something that has put requests with an entity, or you want to write something that you don't want to store in memory, your handlers will be way more complicated. And that's the reason why we created Helidon SE, where we implement these Netty handlers and transform the Netty complicated API into something that is actually manageable by your application. And that's exactly the same thing that every other framework that I know of right now in Java that is favorite is using Netty under the hoods. And they are all implementing these wrappers around Netty to make it usable. So You can use direct netty, but it will be actually a pain. Does it support communication via plain TCP or just HTTP? So in theory, Helidon Nima supports any TCP protocol, but we only implement HTTP, HTTP2, WebSocket, and gRPC. And actually, WebSocket is upgrading from HTTP1, and WebSocket is HTTP2 based. So we didn't see yet protocol that we should implement other than those, but you could implement your own. We are also looking at the future. So HTTP3 is already described, and it's actually not TCP based. It's UDP based, and we don't have yet an implementation in Java that we want to use.
Haha, yes. Yeah, the Nima is made the way that we actually expect that even other servers may use it as the same way as the others are using Netty. The Spring Flux is using Netty under the hood, if I'm not mistaken. Again,
You know, as soon as you start talking about anything that's reactive right now, I hope that we will not have to do that. So is that true if we have bug in reactive programming? We just write this feature again from zero because it's simpler? Sometimes, but we don't. I think Daniel could talk because Daniel is actually responsible for our reactive streams implementation in Helidon, and for the transition, and mostly for the transition between Netty and reactive. We of course don't write it from scratch every time that we have a bug, but sometimes we wish we could. How are exception handlers handled? Well, Jersey is used, so you can use exception handlers in Jersey the same way you would use them with Jersey.
WebLogic.
Or WebLogic, yes. So in general, either you handle it in your code, or you register a handler and with a provider, and it will be automatically handled for you. So it's the same. Is there any plan to support previous versions? We cannot. We cannot support previous versions of Java with Helidon Nima.
And it won't be even the 19, right?
Because Helidon Nima requires virtual threads, and virtual threads are only available since Java 19. When it comes to Helidon itself, we currently have two versions that are in production. It's version 2, which is running minimal version of Java 11, and version 3, where the minimal version is Java 17. The main difference between these two versions is that Helidon 3 has been migrated to support Jakarta packages. So if you use microprofile with Helidon 2, it will be running on Javax packages. If you use it on Helidon 3, it will be running on Jakarta packages, and it's Javas 11 and 17.
Yeah, have you tried to explain the flat map to the junior developer ever? It's way much easier.
And I mean, it's not just junior developers. I was actually preparing a demo where I needed to do a call in parallel to multiple services. And I wrote it in Nima, and it worked. Then I wrote it in our reactive implementation, and I couldn't find a way how to make it parallel. Even if I used an executor service, the outcome was always serial. It was always running in sequence. So I actually had to spend like 15 minutes, on Zoom chat with Daniel to find the correct way to combine these flat maps and executor services to actually run in parallel. So it's not just junior developers. I consider myself to be senior developer, and it's still a problem. Will synchronize block for virtual threads in the future? That was actually a question that was also asked previously, and I talked about this last week with the Java team, and Ron Pressler said that they are working on it, because obviously it is a problem they are aware of. So I kind of hope it will be available soon. In general, synchronized blocks are used in two ways. So first is when you need to do something short term, like synchronization on a list that you want to write to, or on a hash map, and you want to do synchronization to write and read from multiple threads. These cases of synchronization are not a big problem, because 4gen pool can have more threads than just the number of CPUs. So even if you use synchronization, there is a good chance that your server will just work fine. The second problem is, for example, JDBC drivers, which sometimes use synchronization even for some longer-term locking, and that's obviously a huge problem. And again, we see that the industry is catching up. So again, I had a talk with Oracle JDBC driver implementers, and they told me that in Oracle version 21, they have removed all synchronization from the code, and it's only using Java util concurrent locking. And I kind of expect that all the implementations will move that way. First, because synchronization is kind of not a very nice feature in Java, and second, because of virtual threads. I think one last question.
Well, I can do two. Did you compare performance with Vertex? Well, Vertex is performing very similar to the Netty. It's built on top of Netty, but it's very well optimized, so it's just a little slower than the Netty, clean Netty. And there was also what happens if the virtual threads are removed. Well, they won't be removed, Jesus Christ.
I said we made a bet, right? We made a bet that when I saw this description of virtual threads, I said this is what we want, and I really believe that this is the future of Java, and we just went full on it. And if for any reason they would get removed, then obviously we lose half a year of development of our server. And we still have our reactive implementation, so we would continue, but it would be a real pity because I think that this is like the best thing that happened since Java 1.2. So, really hope. I think that we need to finish now because we have just
the coroutines. Well, the coroutines are actually continuations built on top of the JVM, right? It's the library. Well, the virtual threads are continuations under the hood of the JVM. So I didn't measure anything between those two, but just ask yourself which one will be faster.
Okay, for the next questions, we will be here, so you can catch us in the corridor and ask us whatever you want. We will be happy to answer. And with that, thank you very much for your attention, and enjoy the rest of the conference. Thank you.